Alright, so far we were doing Fourier series. And the formulas were the following. First, f of x is a0 over 2 plus sigma, and from 1 through infinity of an cosine, it was n pi x over L plus bn sine n pi x over L, where an can be obtained by this integral, actually 1 over L, negative L to L, f of x, cosine of this function, n pi x over L dx. And then bn was 1 over L, negative L to L, f of x So these were the formulas that we had so far, and we did some examples and saw how using even and odd properties of functions reduced our calculations a lot. Okay? Especially, what I want to point out is that if f of x is even, what would happen? If fx is even, which of the integrals will become 0?
Bn.
Huh? Bn will be 0, because bn's are the odd functions, right? If it's an even function, the even functions will survive here, and the odd functions will go away. So in that case, we will have the function f of x as a0 over 2 plus sigma, n from 1 through infinity of an cosine n pi x over L only. That's it. There's no bn. Okay. Where an can now be this one, because this is even, this product is even, so I can take the half of the interval and double the result, right? So I can do 2 over L integral from 0 to L of f of x, and then cosine n pi x over L dx. Okay. So that's what you can do if f of x is even. Whereas, if f of x is odd, you can say f of x is what? In this case, which ones will vanish?
Cosine.
The cosines will go away. The cosine and the constant term, constants are also even functions. So these are gone, and you're just left with the bn. So you will get n from 1 through infinity of bn sine n pi x over L, where bn now is this one with taking half, and doubling the result. So that's what we know. Now, if you look at the final formulas after taking half of the interval, you realize that you're only using the right part of the function in both cases, right? And that's because if you know that a function is even, then only knowing the right part will automatically tell you what the left part is, right? Same thing here. If you know the right part of the function and you know if it's odd, then you can figure out what's on the left by using the property that it's odd, right? So, interestingly enough, that these formulas can be used. Yes.
For when fx is odd, does it need the a naught over 2?
No, a naught over 2 is an even function. A constant function is, what's a graph of a constant function? It's like this, right?
Yeah.
And that's an even function because it folds evenly. Right? Yeah, so because it's an even function, if it's odd, the cosines shouldn't be there. Okay? So they're both considered as even.
Mm-hmm.
Okay?
So,
All right. So back to what I was saying. If you have a function only defined from 0 to L, you can find the approximate of that function by using either one of those. Okay? You can do that, right? And that is called the Fourier sine series and Fourier cosine series. So let me summarize what the discussion that I just had. I'm saying if fx is a function on 0 to L, okay, then we may extend the function on negative L to L, extend the function to be on negative L to L, so that you can find the Fourier cosine function or Fourier sine function depending on the extension you take. So if you take an even extension, you're going to get a cosine series, and if you take the odd extension, you're going to get the sine series. So then we may extend the function to be on negative L to L as even or odd functions, or as even or an odd function, and apply the left formulas. Okay? Okay, you can use these, and those are called Fourier sine series and Fourier cosine series. Okay, so without further ado, let me show you an example. So here, example 1. Find Fourier cosine series of f of x equal to x plus 2 on 0 to, let's just say 5. Okay, so what I'm giving you is a function. It's like this from 0 to 5. And I'm asking you to find a cosine series that looks like this, which will approximate this function. Okay. Now, why do we want to do that? Well, one is because you will see later that we will be able to use this to solve differential equations. Okay. There are some classes of differential equations that where instead of using a power series solution, you can use these as the solution. Mind-blowing, right? Yeah, but it's possible. There are something called partial differential equations, which we will do later, which will require these type of expansion. So for certain class of partial differential equation, the solutions come in the form of a cosine series or a sine series. That's why you want to do that. Now, there are some other practical purposes. I keep telling you that MP3 players make use of this Fourier series, right? To be exact, the MP3s or JPEG compression, these things make use of the cosine series, not the sine. The reason is if you extend this over to the other side as an odd function, you will get a jump discontinuity, right? If it's odd. So because of this, and I mentioned it very briefly, but every time you have a jump, the approximation does poorly on these jump discontinuities. And you get something called the Gibbs phenomena, which will result in something very messy. But if you extend this function as an even function, you don't get a jump discontinuity. It's connected, right? And think about how you would get if you made this periodic extension. See, really, when you when you approximate this function by a cosine series, you're not really just taking the cosine approximation of this function. You're actually approximating the function, assuming that it's a periodic function, right? So even the extended one, the periodic one, is still continuous. So it suffers less from the Gibbs phenomenon. Okay. So for these JPEG or MP3 players, MP3 file formats, you take the Fourier cosine series instead of the full Fourier series. So those are the practical purposes of doing the Fourier sine series or cosine series. Okay. All right. Anyways, here's the given function, and because it's at Fourier cosine series, we're really taking the Fourier series of the even extension. And actually, if you know which one you're using, then all that's left is just calculation. You just have to calculate two integrals, and that's it. Okay? All right, so let's do it. Okay. A0, solution. What's A0? According to that formula, it's 2 over, what's L here in this context? What's the value of L? 5. 0 to 5. F of x is x plus 2. Since n is 0 here, cosine 0 is what you get, and cosine 0 is 1, so I don't have to put anything there. So this is what I need. And if I calculate, this will be 2 over 5 of 1/2 x squared plus 2x, and then you plug in 5 and 0. Okay, and then let's see, this is 1/5. If I multiply this in here, so 2 cancels, so it's 1/5 of x squared. This times this gives you 4/5 of x. And you're plugging in 5 and 0. When you plug in 5 here, 25 divided by 5 is 5. 5 here, 5 and 5 cancels, giving you 4. So 5 plus 4 gives you 9. So 9 is your value. AN is 2 over 5, 0 to 5, x plus 2. It's the exact same thing, except now n is kept general, n for 1 or more. That means I do need cosine n pi x over 5 dx. That's the calculation I need. And because this is a product of a polynomial and a cosine, you will need to use the tabular or integrate by parts, whichever you prefer better. I like tabular, so I'll use tabular. So x plus 2 differentiates to 1, differentiates to 0. So only 3 lines. And then cosine n pi x over 5 is what I need to integrate. And when you integrate this, remember that n pi over 5 is the coefficient of x, right? This is really n pi over 5 times x. So when you integrate, the reciprocal of this number appears in front. So it's 5 over n pi sine n pi x over 5. And integrating sine gives you negative cosine, and another of this 5 over n pi appears because every time you integrate, this will appear. So you're going to get 5 over n pi squared cosine n pi x over 5. Okay, and therefore, let me just erase this part. Therefore, the integral is 2 over 5. This times this. So it's 5 over n pi x plus 2 sine n pi x over 5. Okay, and then this times this gives you positive, so it's plus 5 over n pi squared cosine n pi x over 5. and you have to plug in the endpoints 5 and 0. When you plug in 5 or 0 into sine, in both cases you're going to get 0. When you plug in 5 cancels and you get sine n pi. What's sine n pi?
0.
0, right? When you plug in 0 here, you get sine of 0. So that's 0 again, okay? So in both cases, I don't have to worry about this. When you plug in 5 here, what do you get? Cosine of? Huh? Cosine of?
Negative 1 to the n.
Yeah, cosine n pi, which is negative 1 to the n, right? So you're going to get 2 over 5, 5 over n pi squared. 5 squared there. I'll just write this as n squared pi squared. Times negative 1 to the n power, because you get cosine n pi. What do you get if you plug in 0? What's cosine 0?
1.
1. So you subtract 5 squared over n squared pi squared. And let's see, if you divide by 5, 1 of the 5 cancel, and 5 is remaining. 5 times 2 is 10. So in both cases, you have 10 over n squared pi squared as a common factor, and you get negative 1 to the n power minus 1. So that's your an. Once you get those an and b, an and a0, what remains is to find the answer in this format. So let's put everything in this format. So 9 divided by 2 plus sigma n from 1 through infinity of this thing. 10 over n squared pi squared, negative 1 to the nth power minus 1, cosine n pi x over 5. Now, it would be nice if I took the time to take a computer program and actually plot this for n equals to 1 through 100 terms or something and compare the two. But I already showed something like that on the video, on the slideshow, right? So on the PowerPoint, I showed you something like that. So what I want to say is that this right side really is an approximation to the left side. And if you chop this series at, say, n equals to 100 or 1,000, the bigger this number is, it will be closer and closer to the left side. Okay. So if you write down the full series, they are actually equal.